So first, let me begin by thanking the organizers for this wonderful conference. And contrary to what some of you might be thinking that we colluded so far as the title is concerned, I assure you that string archaeology has nothing to do with surfaceology except for the logy. Archaeology literally means I'm going to study an ancient problem. And let me begin by a motivational question. Typically in quantum field theory, we start off by drawing the S-channel diagram or T-channel diagram. So let's imagine that we are scattering colored particles, and we have just two channels. So there is an ST permutation symmetry at tree level. And in string theory, these lines fatten up and give you a world sheet. And instead of two channels, there is a way to deform the first figure into the second figure, and so you don't really add these channels. So this diagram is enough to calculate both these diagrams. So this goes by the name of dual resonance hypothesis, where the S channel is equal to the T channel. So I took this from Wheaton's Snowmass review from 2001. 2001 was selected because that is the year that I started my PhD, and most of you were babies. So when we try to set up a non-perturbative description of the amplitude, the ancients told us to focus on dispersion relation. So this is the simplest dispersion relation. This is an unsubtracted fixed T dispersion relation. This is just a fancy application of Cauchy's residue theorem. In this particular case, it's a straightforward application. So what we do is we hold the second variable T fixed. So that's why it appears in the discontinuity of the amplitude as well, and then we integrate over the first one. So this is what is called a fixed T dispersion relation. You can also consider the fixed S dispersion relations. The question is that this figure here suggests that there must be a way to deform the fixed T into a fixed S dispersion relation. And if there is such a dispersion relation, then what is the deformation parameter? So here you can think of the deformation parameter as some kind of a stretching parameter that enables you to stretch and deform this diagram into this diagram. So in other words, can we come up with a string flavored dispersion relation? The answer is yes, and so that's going to be the focus of my talk. So this is based on a series of papers that we have been working on over the last decade or so. So this is going to be, my talk is going to be based on the first of this paper, which was written with a postdoc in IISc, and the second one, which has this picture, which I'm going to explain in a little bit, which was written with Faizan, who's there in the audience. And in fact, I should point out that he's on the job market, and another graduate student of mine, and Arnav, who is a postdoc with me. And this uses heavily technology that we developed in earlier papers. And I should also point out that this line of questioning did not originate by thinking about string theory, rather it originated by thinking about critical phenomena or the conformal bootstrap, in particular so far as the epsilon expansion is concerned. And this is something that we were doing with Rajesh and some of my graduate students. This picture is the answer to the question that I posed in the previous slide. So this is going to give you a unified dispersion relation, and there is going to be a parameter in the dispersion relation, and depending on what you do to the parameter, various limits correspond to all the known dispersion relations that we have. So fixed T, fixed S, and fixed U are familiar to you. CSDR stands for crossing symmetric dispersion relations, which is less familiar to you, but this was actually briefly examined in the 1970s. And L stands for local crossing symmetric dispersion relation. This was built over the last couple of years. So this is the outline of my talk. I'm going to review the bootstrap origins of string theory, like what I told you that I'm going to talk about archaeology, so some ancient ideas of string theory. I'll explain what the puzzle in the string literature is. And then I'm going to introduce the local crossing symmetric dispersion relation. Unfortunately, I won't have time to show you how it is derived. The derivation is a little involved. And then I'm going to introduce this parameter lambda that was there in the web of dispersion relations figure. And I'm going to give you a simple explanation why this parameter is expected by exploiting field definitions. And this is an idea motivated by string field theory calculations, and I'll only briefly explain where that motivation comes from. And then I'm going to set up the bootstrap keeping in mind tree-level string theories using semi-definite programming and machine learning, and I'll explain why machine learning is of use in this particular case. And finally, in the last slide, I'm going to talk about a closed string and a KLT type relation with level truncation. So let's review the Bootstrap origins of string theory. So this goes back to depending on where you do your string theory courses. So by a show of hands, how many of you have done a formal course in string theory? Okay, it's less than half the audience. So depending on where you do your course, so Daniel and I did it in Cambridge, so we learned it from this textbook written by, did Michael teach you string theory? Anyway, so if you read the introductory chapter, then they talk about this dual resonance hypothesis where you don't sum over channels like you do in quantum field theory, but one diagram is enough. And in fact, if you read the introductory textbook very carefully, the introductory chapter very carefully, then there is a very interesting line. The duality hypothesis never had more than a slender experimental support, and the Veneziano model was merely an ad hoc way of satisfying this not so well motivated hypothesis. So it's very curious. So if you actually go back and read Dolan Horn Schmidt, which actually started this dual resonance hypothesis, you will realize that they were really honest. They actually proposed two different resolutions to the analysis of experimental data, and this was one possible resolution. Now, here there is already a sort of a contradiction with the modern understanding of string theory, because we now have string field theory, and string field theory is just a version of quantum field theory in the string picture. And in this framework, we actually do have these channels. You have separate channels, and you do need to add both the channels. So how do you resolve this apparent contradiction? And before I go to explaining this a little bit more, let me point out that there are several confusing statements in the older literature which have, in my mind, never been completely clarified. So one, for example, if you look at this beautiful physics reports article by Stanley Mandelstam, dual resonance models, he actually distinguishes how to think about hadron physics. He says that elementary particles you would sum over channels, but if you think about scattering composite narrow resonances, you would either sum over T channels or S channels. And if you look at some of the literature which was reviewed in this, again, a beautiful textbook, The Birth of String Theory, then you see various famous people talking about a phenomena called double counting, because if this was already equal to this, and if you try to write down a version where you're adding both channels, then there would be some kind of a double counting, because this has already taken into account what happens in the other channel. So the same thing is echoed many times in this review, which was, I think, put out in 2011. So this is what you would do in string field theory. You would actually, suppose you, for argument's sake, focus on the sphere diagram where you're doing closed string scattering amplitudes. Then in order to actually decompose in terms of channels, what you would use is what is called the plumbing fixture construction. And this is something that is already mentioned in Polchinski's textbook, volume 1 and chapter 9. You would actually tear apart the single sphere where you have vertex operators inserted, and you would glue them back together using propagators. And when you do that, you get all the 3 channels that you would expect. This is 3 channels because this is closed strings, and you have 3 channel symmetry in this picture. Most of my talk, I'm going to focus on something that has only 2 channels, like gluon scattering. And what happens here, the main lesson, I'm not going to go through any of the details of this calculation, is that you need to make a local choice of coordinates when you're doing this plumbing fixture construction. And in the local choice of coordinates, after you have exhausted all the conformal symmetry available to you, you still have a residual parameter here, lambda, and lambda can take on any value. In this particular case, it's a free parameter, and its value has to be bigger than 3. The reason why it has to be bigger than 3 has to do with this figure. So the moduli space of the construction, you have to cover the entire moduli space. So if you just add 3 channels, then you don't cover the entire moduli space. The white region is left out, and you still have to add what can be interpreted as contact diagrams to cover this entire moduli space. So the only singularities that are present at tree level in this picture are the poles that come from the usual quantum field theory arguments. The white region needs contact diagrams, so it is not sufficient to just add channels. The contact diagrams play a crucial role. Now, very strangely to me, the first time that this was ever explicitly demonstrated, for example, for the Virasoro-Shapiro amplitude, was in a paper by Ashok Sen from 2019, where he had a formula for these contact diagrams, and that formula was in terms of a regular integral, and that integral could only be evaluated numerically. But the key fact is that there is a parameter that is left over, and the contact diagrams dependent on this parameter lambda. So let's, sorry, giving away the secret, the other way around. So what are the series representations that are known in the standard maths literature? So let's go back to the open string scattering amplitude, the Veneziano amplitude. So this is just the Euler beta function. So what are the series representations that are known? So there are the usual series representation where you exhibit only the poles in one channel. So the first series only has poles in one channel, but then you pay a penalty. This series only converges if the real part of S2 is less than 0. And similarly, you can exhibit the poles in the other channel, and the penalty you pay here is the real part of S1 is less than 0. Now, what might be going through your mind is that why don't we just take half of one channel or half of the other channel and add them together? And the reason why that is not going to be a good thing to do, because that series would only converge when both the real part of S1 and S2 would be less than 0, and so the poles would be invisible in that representation. So the other less familiar representation is what in modern terminology can be called the fixed U representation. And that is a series representation for the Euler beta function, where apparently you have two channels because you have poles in both the channels, and rest by a polynomial factor. So this object here is what is called the rising factorial, or the Pochhammer symbol. It's a degree n polynomial. So if you see an n as a subscript, it becomes a degree n polynomial of whatever the argument is. So here also you have that feature that it is a degree n polynomial of this object. But again, here you pay a penalty that the real part of S1 plus S2 has to be bigger than -1 for this sum to converge. And what is very funny is that this last series representation can be easily worked out if you open Grashchan and Rijek. So when I was doing a PhD, we didn't have Mathematica that prevalent. We used to rely on this huge fat textbook which were used for weightlifting or paper weights. And if you open that, you would be able to easily work this out. But for some very strange reason, this last formula is rarely mentioned in the string literature. And I should point out that neither of these standard series representations meets the string field theory expectation, which says that the only non-analyticity should be at the poles because of this restriction that are here. And more importantly, neither exhibit this parametric ambiguity. So there is no lambda in this, or an analog of lambda in these series representations. So what is the resolution? So the resolution is a new series for the Euler beta function, which Arnav and I worked out in this paper here. And I should point out that the mathematicians have found an independent proof of this series representation. So Halmar Rosengren, who's a Swedish mathematician, has found independent proofs, not relying on the fancy new dispersion relation that I'm going to talk about, but using standard methods based on partial fractions. So let's go through the new series a little bit. So you have here sum over both channels. Here explicitly you see the poles in both channels. Crucially, you have a regular piece, and it is dressed again by a polynomial in S1 and S2. And of course, as I've been harping, there is an extra object that comes here, this extra parameter lambda, which is going to play a crucial role in sort of extrapolating to various limits. And so in this particular case, you get the Euler beta function for any value of lambdas, so long as the real part of lambda is bigger than 0. So you could actually plug in a complex parameter here, and you still get the Euler beta function. So I have already mentioned these 3 points. So the other points that I should emphasize is that this kind of a series representation does not exist in the mathematics literature, and this forms a generalization of the hypergeometric series. And the reason why it does not exist in the mathematics literature is because we use a local crossing symmetric dispersion relation in 2 channels, which did not exist before our work. And if you plug in various values of S1 and S2, for example, if you set S1 equal to -half, S2 equal to -half, you get pi. And so this actually gives you a new series representation for pi, which did not exist in the mathematics literature either. And you can do a low energy expansion of this object and you'll get similar parametric formulas for the zeta functions. So what are some of the other reasons? So there's another point that I forgot to emphasize, is that you can truncate this series. So for example, suppose you took only 10 terms, then all the kind of stringy features that you expect from the string theory amplitude are visible in this representation. So in particular, you'll see the reggae behavior, and you'll also see the exponential softness, because this series actually converges for any value of S1 and S2. This is another use why you would want to have such a representation. So if you were to study this fascinating problem, we know that string perturbation theory is going to break down. So if your center of mass energy was bigger than this object, G string here is a string coupling, then if string coupling is held small but fixed, then at some energy scale your string perturbation theory is going to break down. And suppose you were interested in studying this problem, then you would desire to have a series representation which was valid up to some energy scale, and after which you would use dispersion relations. So let me flash the formula. So as I said that I'm going to use a fancy novel dispersion relation, which unfortunately I don't have time to explain how it was derived. But this is the dispersion relation, and it has got some very interesting features. So let me just point them out. So here is your amplitude of two variables. It is permutation invariant if you interchange S1 and S2. So we want to see that explicitly in this form. So you do an integral, so the integral starts from where the first pole is. Then there is this piece here. This piece should remind you of something. This is very familiar if you do phi cube theory. And then this could be interpreted as a contact term. So you can think of this as sigma as playing the role of the mass, and you're integrating over all possible masses. Curly A here is the absorptive part. Now, contrary to the fixed T dispersion relation, where the second argument here would be S2, suppose you are taking the absorptive part in the first variable, the second variable in the fixed T dispersion relation would be S2, but in the local crossing symmetric dispersion relation, this is replaced by another object, S1, S2 divided by sigma. So that is a difference from the fixed T dispersion relation, because fixed T you wouldn't have this term or that term. You would just have the first term and this absorptive part and the second argument being different. I will only focus on examples where this will be the main, this object here, not the last term or the first term. The first and last term will cancel in whatever I'm going to say. So for example, where would you see this combination? Because I said that there is a Pockhammer, and the argument of the Pockhammer had this S1, S2 divided by n. It's very easy to see where that comes from. You start with the beta function, and I've exhibited it in single channel expansions because it's easy to read off the residues. So you would calculate the discontinuity of this amplitude in the S1 variable. There's a simple pole, so the discontinuity becomes a delta function. And then the rule is that the S2 variable you replace by S1, S2 by sigma, so that the absorptive part here simply becomes a sum over delta functions weighted by this polynomial, and this is where you see this S1, S2 divided by n. So far, in the formula that I just now showed you, there was no existence of lambda. So where is this parameter coming from, which will enable me to stretch the dispersion relation, deform the dispersion relation from the fixed T to the fixed S and other forms. So why should we expect a parameter in the first place? So let me give you a simple argument. So let's say that, let's consider a toy problem where we have light particles phi1 and phi2 and some heavy particles psi1 and psi2. So let's consider the scalar situation, and let's say one of the interactions was phi1, phi2 times psi2, so the light particles are interacting with the heavy particle. Now let's redefine. So let's redefine the heavy field in terms of the light field. Let's consider this redefinition psi2 going to psi2 plus lambda phi1, phi2. And when we consider a series representation and we truncate, what we effectively do is that we actually drop all the fields that are there in the Lagrangian corresponding to the heavy modes. But if you started off by first doing the field definition, which would introduce a new term in the Lagrangian which involves only the light modes, because of this redefinition and you have a cubic coupling, you'll have a new contact interaction which depends on this redefinition parameter lambda. You would have a contact interaction that was generated because of this redefinition. And the truncated version of your amplitude would actually now be sensitive to this field definition parameter. So typically, when you do field definition, your amplitude is not dependent on the field definition parameter, but if you truncate the Lagrangian, it would. So the lesson that we learn is that if we truncate the heavy fields, then the observables involving only the light fields will know about the heavy guys through this ambiguity, and this is the parametric ambiguity that I expect in this series. So how do we introduce this, this parameter in the series representation? So far as string theory is concerned, we used this trick. There are multiple different ways of doing this. So the trick that we used was the following. So we used this new dispersion relation, and what we did was, instead of starting with the Euler beta function, we slightly deformed it. So we introduced these parameters alpha and beta. So the Euler beta function was when alpha and beta were both 0. Then we plugged it into this dispersion relation that I showed you, and we noticed that the left hand side actually has a symmetry. Takes time for the to appear. Yeah. So the left hand side has a symmetry. So notice the symmetry that if alpha goes to alpha plus lambda, but S1 also goes to S1 plus lambda, along with similar transformations, then the left hand side has a shift symmetry. And what happens is that when you plug this into the dispersion relation, each term in the dispersion relation does not have this shift symmetry. The entire sum has its shift symmetry, but each term in the sum does not. And that is how we introduce this parametric ambiguity. There are two different ways of doing the same thing, and unfortunately I will not have time to explain either of them. So you can introduce this parameter lambda either by using this local crossing symmetric dispersion relation, or using this partial fraction method, which was introduced by Halmar. So here is the formula again, and now we are going to take various limits. So here is a series representation. So you have the two channels plus this regular term. Now the first thing to observe is that I told you that this series converges for any value of S1 and S2 away from the poles. So we are allowed to set lambda equal to minus S1 or minus S2. So let's say we set lambda equal to minus S2. So immediately you see that this term and this term cancels out. And if you set lambda equal to minus S2, this goes away and you get 1 plus S2 Pochhammer n, and which is precisely the fixed T or the single channel representation that is known in the maths literature. Similarly, you can do it for S2. To see the fixed U representation where you have the two channels, but then you have it being dressed by something that look like linear in S1 plus S2, all that you have to do is take the large lambda limit of this summand, and you will see that you will get precisely that form. So three different limits actually take this representation and match it up with whatever is known in the maths literature. So this gives you sort of this kind of a feel that you are allowed to actually truncate and still capture all the essential features of the string amplitude. So you should be able to write down an effective action of this kind. And the other advantage is that, as I told you, you get a new formula for pi, which actually looks like this. You can play around, you can actually have fun with pi. So we calculated pi to many thousand decimal places. Using this, it's completely useless because it's not one of the fastest converging series, but this is the picture for pi that you have. So lambda controls the rate of convergence. So the picture actually tells you that neither extreme values, when lambda is small or lambda is very large, actually gives you the best convergence rate. It is somewhere in the middle that you get the best convergence rate for pi. So this is an example. And in fact, in one of the limits, you get the first ever series representation that was ever written down for pi, which goes by the name of the Madhava series. In case you don't know, in the Western world, it is called the Leibniz series, but Madhava reached there 200 years before Leibniz. So it's called the Madhava series. And I would like to call this holographic pi because there is sort of an extra dimension that lambda introduces. And it caught the fancy of popular level people. So this got covered in Scientific American. But I I should just point out that if you drop the I, then it has a very unfortunate form. Yes. So I'm going to, in the remaining few minutes that I have, I'm going to briefly talk about the string bootstrap, how you're going to use all this to set up a new way of doing string bootstrap. And I should point out there's a lot of work in recent times. There are papers written by Utin, who's there in the audience, and we found those papers very inspirational in framing some of the questions that we asked. So what we are going to do is we are going to actually use a basis that is motivated by this unifying dispersion relation. So now I have presented it in a unifying manner rather than actually exhibiting it for the particular case. So you have these two channels, you have this regular piece, and now you have the S channel discontinuity, and the T variable in the S channel discontinuity gets replaced by this, this object here. And it's again very easy to see that various limits that you take at the level of the dispersion relation itself gives you fixed T, fixed S, and fixed Q, and you also get the associated convergence domain that are indicated here. And just to point out, there are two other dispersion relations that are less familiar. The crossing symmetric dispersion relation also can be recovered by choosing a particular value of lambda here, as well as the local one. And of course, once you have this parameter that gives you this kind of a picture, it's very tempting to think that maybe there is a way to sort of ask the following question: how do you get a world sheet, or under what circumstance do you get a world sheet from the solutions of the bootstrap conditions? So in this paper that we put out very recently with Faizan and students and Arnab, we wanted to consider a general class of amplitudes that arise from this dispersion relation with integer poles, but with this field definition ambiguity. So remember that lambda here, although it controls the rate of convergence, ultimately if you summed over all modes, the lambda dependence goes away. So lambda is a fictitious parameter so far as this representation is concerned. So the derivative of this amplitude with respect to lambda would actually be 0. So any derivative of this amplitude with respect to lambda would be 0. So the basis that we are going to consider for the new way of doing the tree-level string bootstrap is this. So everything is fixed. So these are the Gegenbauer polynomials. Everything is fixed. So lambda can take on sort of arbitrary values. The only things that are not fixed are the coefficients here, these CNLs. Unitarity, tree-level unitarity tells us that these guys have to be positive, and that's all that we're going to use. How do we constrain? And we are going to constrain a little differently than what is done in the literature. So what we are going to do is, this is our bootstrap problem. So first of all, we are going to subtract off the massless pole call this amplitude m bar. We are going to fix some low energy Wilson coefficients. So this is going to be the coefficient of S1 plus S2, and this is going to be the coefficient of S1, S2. And what we're going to minimize is the m bar 0, 0. And why are we doing that? Because it can be shown that physically we are minimizing the first finite moment of entangling power. And this is also something that I don't have time to explain, but this is a sort of the motivation why we decided to minimize this rather than actually look at kinks in the space of Wilson coefficients. And let's say we fixed these Wilson coefficients to the known superstring values. Then what happens is that this minimization problem, along with the condition that this m bar should be lambda independent, it surprisingly gives you the values of the CNLs which are very close to the superstring values. And this is at this stage that machine learning helps. And why does machine learning help? Because we want to truncate the modes. And when we truncate the modes, automatically the spin sum also gets truncated. So basically the independence of lambda is up to a tolerance, and that tolerance is arbitrary. So the physical way of imposing the tolerance is to demand that the absolute value of 1 minus the value of the amplitude at some lambda 1 and a different value of lambda 2 is less than some tolerance that we can specify. And this has to be done on a grid of points S1 and S2. But this condition is actually a nonlinear condition. You cannot multiply through by m because you don't know the sign of m. So this is what you want to solve. And this can be efficiently done. So the first attempt that we did was to sort of put in an ad hoc tolerance. And I'll just give you a couple of random examples. So if you look at the first leading trajectory that you get, so let's focus on n equal to 11, then you can see that the expected value and the numerical value that you get from the bootstrap are very close. And similarly, you can look at the second daughter, and then you can compare that. It's reasonable, it's not exact, but then it's reasonably close to what you expect from string theory. So this is the picture that you get. And these blue shaded region are amplitudes which happen to obey this dual resonance condition very well. So in fact, right through this middle of the blue region, there is a black line, and this corresponds to hypergeometric deformation. So the open superstring case, this was written down by Marcus and his student very recently in 2024. And this passes through the center of R allowed region. But there are other interesting amplitudes which do not appear to obey this dual resonance condition well. And so those are the interesting things to consider. So we implemented, instead of specifying this ad hoc tolerance, we use machine learning as well. So we ask the machine to learn a function, two variable function, a function of spin and n. One of the advantages that we have now is that the machine actually doesn't know that ln n are integers, that the constraints that we feed in are for integer ln n. So basically you can try to study Regge theory, where you can complexify the angular momentum, and when you do that, you seem to reproduce the alpha t that is expected from string theory reasonably well. The intercept is very close to -1, which is the correct value. The slope is not close to -1, which is the correct value. It's more like -0.6 or something. But this way of doing things potentially opens up the way to do Regge theory by looking at the complex L plane. So last slide. As I said, I'm going to tell you about a similar formula for the closed string. So this is the Virasoro-Shapiro amplitude with the kinematic factor stripped out. So it has a similar form. So there is going to be a lambda. Now it's going to be 3-channel symmetric. So you'll have S1, S2, and S3. The dressing factor looks like a Pochhammer, and you worry that there's a square root, and so maybe this is not a polynomial. But very surprisingly, when you actually simplify this, this does work out to be a polynomial. So despite appearances, all the square root drops out. And what you can do is you can actually subject it to a level truncation. So you can truncate the level, and you can ask what happens to this expected KLT condition. And this is where, had you summed over all modes, you would get a new representation for zeta 2. So this actually is zeta 2 if you sum over all modes. And so this also has the flavor of doubling up. So there is the square factors here that you might have anticipated. Now, if you truncate, then then you can actually compare the first massless term, and that this is expected to agree. The second term only agrees if this guy and this guy cancelled. And so now the cancellation is not going to be exact if you truncate, but what you can do is you can modify this kernel factor here, this sign, the product of sines divided by sine. And maybe with a modified kernel, you can actually restore this KLT relation level-wise. So these are my conclusions. I just went a little over time, I guess. Thank you for your attention.
Questions?
So when you say level truncation, but you say level truncation, but I see that in your sum you still have infinite sum over resonance. So where is the truncation?
You can actually truncate that sum. You don't have to keep infinite sums. So actually you can perform the analysis with a finite number of modes.
Okay, but the formula itself is still, there's no truncation in the formula.
Yeah, there's no truncation in the formula.
So you're doing machine learning, so you're doing lambda, so that's different from the
Yes.
lambda in the usual step.
Yeah.
Require. So I would imagine that when you do the reward, that you're connecting 2 lambda points and that it's smaller than some value.
Yeah.
But you could have chosen multiple different lambda.
Yeah, that's true.
How do you determine what is the optimal reward?
So what we did was we looked at a pair of certain pairs of lambda values, and then once we got a solution that did not deviate too much, the CNLs were sort of similar. We decided that that's the correct solution. So there are two different ways. We also looked at derivative conditions, and we can talk. I can explain in private, or tomorrow I can explain to you what we actually did. David.
Do you have a systematic way of introducing these lambda type terms in more general hypergeometric series?
Yeah, so I think the systematic way is through the dispersion relation. Um, so our take would be that you start out with the dispersion relation, and these dispersion relations work for any function that has a specific fall-off at infinity. So if it is a two-variable function and it respects a specific fall-off, you would be able to introduce this.
5-point or 6-point?
Oh, I see. No, I don't have a systematic way of doing that. But the partial fraction method that Rosengren has introduced recently, that I believe might be more suited to answering those 5-point and 6-point.
Okay, in view of time, let's thank Aninda again and it's available.